Okay, let's now go through the 2017 Electrical Systems exam. Describe what is meant by the term time constant. Well, the time constant is the time it takes for a 63% change in either the voltage or the current in a circuit. That is just something you're going to have to remember. It's not given to you, so let's write that down. The time taken for a 63% change in either current or voltage. Okay, so moving down, we have a circuit, we have a resistor, and we have a capacitor. We're given a voltage here, a capacitance, and a resistance, all of which will undoubtedly come in handy, as well as an energy there. And we're asked to calculate the energy stored in the capacitor when it is fully charged. So that's the energy that the battery supplies overall, and we now want to find only the energy stored in the capacitor. To do this, we have an equation for energy given on our formula sheet, which is half CV squared. And since we know both, we can just plug in our numbers. Which gives me 3.6 times 10 to the minus 4 joules. Okay. Explain why this energy stored in the capacitor is less than the energy supplied by the battery. Well, in this circuit we have a resistance, and what a resistor does is it takes away energy, electrical energy, and converts it into heat. So our culprit is the resistor. So let's write that. The resistor consumes electrical energy and converts it into heat. Alright, draw a graph of circuit current against time for 15 seconds after the switch is closed. Data points should include the initial current and the current after one time constant. Okay, so the first thing we need to know is exactly what the time constant is. And on your formula sheet, you will find the equation that the time constant is equal to RC. Where we know both, we're given it in the above diagram here. 8 times 10 to the 5 our resistance, and 5 microfarads, or 5 times 10 to the minus 6. So let's write that. Which gives me 4 seconds. Okay, so we need to basically plot points for every time constant, and that will allow us to sketch a graph. So we know that one time constant is going to be here at 4 seconds, 2 time constants at 8, and so on. Okay, now we need to find out what the current is for each time constant. So at our first time constant, the current will have decreased by 63%. So we need to first now find our maximum current, which we can do using our simple Ohm's law, V equals I R, where we can rearrange that for I, which is V over R, where our voltage was 12 and our resistance was 8 times 10 to the 5, which gives us 1.5 times 10 to the minus 5 amps. Okay, so we know that our maximum is going to be our 1.5 here. So we know there's a point there. We now need to find what a 63% reduction in that is going to be. So the easiest way to do that is if we recognize that if we start from a value and we reduce it by 63%, what we have left over is going to be 37%. So if we find 37% of our 1.5, we'll find what the current will be after a time constant. And then if we find 37% of that, we'll find what it will be at the second, and so on. So at our first time constant, we're going to have 0.37 times 1.5, which gives me 0.56. Okay, for our second time constant, we're going to have 37% of that, so 0.37 times 0.56, which gives me 0.21. For our third time constant, we're going to have 0.37 times 0.21, which gives me 0.078. And finally, for our fourth time constant, we might as well do that. We're going to have 37% of that, so 0.37 times 0.078. which gives me 0.029. Okay, so let's plot all of these points. So our first time constant is at 0.56, which is about here. Our second time constant is at 0.21, which is about here. Our third is at 0.078, which is about here. And our last one is at 0.029, which is going to be about there. Okay, so let's see if we can sketch this as nicely as possible. All right, that's not bad. Okay, explain why the graph has the shape you have drawn. Okay, so what we're seeing is that the rate of change of current is really high initially, and then it peters out and slows down as we continue on. So the reason for that, if we can think about our parallel plates, if our plates are really charged, they have a lot of charges on them, then they're going to repel significantly other charges. But the less charge you have on these plates, the less repelled the charges will be. So it's like they're all bunched together and pushing against each other. And initially, when you break those floodgates, they all come piling out because they're all repelling each other. So let me try and put that into some coherent sentences. The current is initially very high as the plates are at their maximum charge and repel outgoing charges. As the plates discharge over time, they repel outgoing charges less, resulting in a lower current. Okay. The time constant of the RC circuit can be changed by adding a second capacitor, as shown below. Explain how this affects the time taken for the capacitor to charge up. So, there are a few steps of reasoning here. Firstly, when you add a capacitor in parallel, as we have done here, you increase the capacitance. So let's write that. When you add a capacitor in parallel, you increase the capacitance. Now, the next step here is that via our equation for our time constant, tau equals RC, you can see that if we increase our capacitance, our time constant must also increase, which increases the time for the capacitor to charge up. So let's write that. Via this equation, when you increase the capacitance, you increase the time constant. This therefore increases the time taken for the capacitor to charge. All right, let's move on to question 2. So we have a car engine, an induction coil that's designed to produce a very high voltage spark. We have a nice little circuit diagram here, and we're given some value, so we know that it's 8,000 turns there. So the induction coil has 50 turns in the primary coil and 8,000 turns in the secondary. Cool, so we have our ratio. And it's all simplified in this circuit here, which is a lot nicer to look at. We have a graph of the current and time, which is cool, and we have a solid line there. All right, state the value of the voltages across the ideal inductor once current has reached a maximum value of 5 amps. So, inductors produce an opposing voltage when the current is changing. If the current is not changing, such as when it's reached its maximum, then there will be no induced voltage. So, 0. All right. Explain why the current does not immediately reach maximum value as soon as the switch is closed. So let's look at what's going on here. So we have an inductor in a circuit, and there's a number of ways to look at this, but I'll try to break it down as step by step as I can. So as this current starts to charge up, a magnetic field is established inside this inductor. As the current is changing, as it's increasing, we have this magnetic field being established. Now, as that magnetic field is established, the magnetic field produces an opposing flux, which creates an opposing voltage in the circuit. So as the current is increasing, this inductor is producing a voltage to oppose that. So let's try and write that down to something coherent. As the current increases, a magnetic field begins to build in the inductor. This changing magnetic field induces a voltage in the inductor that opposes the increasing current. Okay. Immediately after the switch is closed, the back EMF across the ideal inductor is 12 volts. Using the dotted line on the graph on page 6, calculate the self-inductance of the ideal inductor. So we know that our EMF is 12 volts. And the equation that we're going to be interested in is on your formula sheet, and it is that the EMF is equal to negative the self-inductance multiplied by the rate of change of current. So we are wanting to find our inductance. We know our EMF, and we can find the rate of change of current here on our graph. So we can see that let's take it between these 2 points just to make it easy on ourselves. We can see there that our change in time is 0.1 seconds and our change in current is 6 amps. So let's write that down here. Now let's solve this equation for our self-inductance. And I'll do that by first multiplying both sides by the change in T and dividing by the change in current. And next I'm going to swap these sides around and multiply both sides by -1, so my self-inductance is positive. Now, the negative sign here is just to show that the change in current is in opposition to our back EMF here. So to make everything work out nicely, we just need to make one of them negative. And for convenience, I'm going to make our back EMF negative. So let's put our numbers in, which gives me 0.2 and units of henries. Okay. Sparks require a very high voltage to be produced. Explain how it is possible for a spark to be produced across the gap in the spark plug when the switch is opened. Now, if you recall back to how I was describing the behavior of an inductor, we get a back EMF in our inductor when the current is changing. And furthermore to that, via Faraday's law, the greater the rate of change of current, the greater the induced voltage. So if we were to open the switch here, we would get a rapid drop in current, and that rapid drop in current would be met by a high voltage back EMF from this inductor, which makes more sense to look at this diagram here, which would produce a spark over there. So let's try and make that coherent. When the switch is opened, the rate of current flow drops rapidly. This causes the magnetic field in the inductor to collapse, causing a rapid change in flux and consequently a very high back EMF or opposing voltage. Alright, on to question 3, and Thomas is using a parallel plate capacitor with wood as a dielectric to measure water content in the wood. So we have a basic circuit here. We can see that our wood in between our parallel plate capacitor is serving as our dielectric. A bunch of values here which I'm sure will come in handy. And we're asked right off the bat to calculate the peak voltage of the AC supply. So On your formula sheet, you will see that our peak voltage, our Vmax, is equal to the square root of 2 multiplied by our VRMS. And so up here we're given our RMS voltage, which is 12, so we just need to plug in our 12, which rounding to 3 sig figs gives me 17.0 volts. Alright, and now we need to calculate the RMS current in the circuit. Now, to do that, first let's start off with this equation that you're given on your formula sheet, V equals IZ, which states that the voltage is equal to the current multiplied by the circuit's impedance. And the impedance, if you recall, is a combination of the resistance of the circuit and the reactance. Resistance and the reactance. Now, the equation for our impedance is the square root of our reactance squared plus resistance squared. Now, knowing both, we can just put our numbers in, which gives me 55.2 ohms. Okay, and given that we also know our voltage RMS, so to be clear, our equation is that our VRMS is equal to our IRMS times Z. Now, because we're wanting to find the current here, we can rearrange that by dividing both sides by Z. So we get that our RMS current is equal to our voltage RMS divided by our impedance. Putting our numbers in gives me 0.217 amps. Okay. Explain what would happen to the circuit current when the wood in the capacitor is replaced by a similar piece of wood that contains more water. So in looking at this question, there are two equations I want to consider. The first is for our capacitance, and the second for our reactance. Alright, unfortunately I just explained this all while I wasn't recording, so let me try that again. So, if we increase our relative permittivity here, via this equation, our capacitance will increase. If our capacitance increases, then via this equation, our reactance must decrease. And if our reactance decreases, then via this equation, our impedance must also decrease. And lastly, if our impedance is decreasing and we have the same voltage, then our current must increase, which is what I've described here. Okay. So we have an inductor in series with a capacitor and resistor. The reactance of the inductor, we have that at a certain frequency, and we have the reactance of the capacitor at the same frequency. And Thomas adjusts the frequency until the current is at maximum, which is the resonant frequency, which we need to calculate. Now, for the resonant frequency, the first thing to unpack from that is that our reactance of our inductor must equal the reactance of our capacitor. And further to that, we can substitute the equations for each of those, which you'll find on your formula sheet. And what I'm now going to do is try to solve for our angular frequency. So I multiply both sides by our angular frequency, and I'll divide both sides by our L, which gives me this. Now I can square root both sides. And our angular frequency here can be expressed in terms of our plain old natural frequency as 2 pi f. And if I divide both sides by 2 pi, I've solved for my frequency. Okay, the problem here is that I need my inductance and I need my capacitance. Luckily, we're given the information right here that we need to work either out. So our equations that we just substituted can be used to find our capacitance and our inductance. We'll start with our inductance. So we know that our XL is equal to omega L, or 2 pi FL. If we want to solve that for L, we just divide both sides by 2 pi F, and we would get that our L is equal to our XL divided by 2 pi times our frequency. We're given our reactance, that is 35.7, and our frequency is 151 Hertz, which gives me 0.0376 Henry. Okay, now for our capacitor, we can do the same, but our equation for capacitance is a little bit different. Now, with a bit of rearranging, we can solve that for our capacitance if I multiply both sides by C and then divide both sides by our reactance. Where our angular frequency is, of course, our 2 pi F times our XC. And I can just put my numbers in now. And that gives me 4.5 times 10 to the minus 5 farads. Okay, now going back to this equation here, I can now plug in all of my numbers, which gives me 123 Hertz. All right, explain why the current is maximum at the resonant frequency. Okay, so at the resonant frequency, our reactance of our capacitor and inductor are equal, but they're also in opposition to each other, and they cancel out, which leads to a minimum in impedance and therefore a maximum in current. And we kind of already explained this in the previous question, but hell, let's go over that again. At resonance, XL and XC are equal because they are out of phase with each other, they cancel out, and the total reactance becomes 0. This means the impedance is at its minimum possible value, that is that Z equals R, and our current is thus at a maximum. Okay, and that's it.